Showing the correctness of the reduction in the other direction is somewhat more challenging and kind of more fun, for the right value of fun, which might be 0. So we want to argue that if there is an Hamiltonian cycle in the given graph, then by necessity the original formula is satisfiable. Okay, so to this end, we first need to argue that the Hamiltonian cycle cannot do any shenanigans. So what do I mean by shenanigans? It cannot do what's drawn here in the graph, right? It comes on a row, then jump to a closed vertex, and then leave on a different row. Because that would be bad for us, because we really want the Hamiltonian cycle to traverse every row from left to right or from right to left consistently without going to other rows on trips that are not relevant. Okay, so how do we show that? So the key idea is that if this happened, if the Hamiltonian cycle returns to a different row, then the next vertex of along the original row that it came from, this node is now no longer accessible. It's an orphan. Why is that? Well, think about what the cycle is going to do. It's going to do whatever, travel in the graph, right? But then somehow it has to arrive to this vertex, right? It has to, because it's a Hamiltonian cycle. It needs to visit all the vertices in the graph. It cannot come from this vertex, the closed vertex, because the Hamiltonian cycle already used this vertex and it cannot visit it again. So this edge is bye. Similarly, this edge here, the incoming edge here, from the left side is also gone. So, so the only way this edge is gone, this edge is gone. In fact, both edges here are gone. The edges, it cannot use the edges in this direction, it cannot use the edge in this direction because this vertex is visited. This edge is gone. So what happened is that in the remaining graph, this vertex now is a singleton. It's essentially has those two edges are no longer usable. It has only one incoming edge, right, and one outgoing edge, both of them connected to the same vertex. The Hamiltonian cycle cannot come in here and then escape, because that would require visiting this vertex twice. So that's not possible. So if the Hamiltonian cycle tried to divorce its current row and go on a different row, it's just not going to work. No cheating on rows by the Hamiltonian cycle. So that means that really the Hamiltonian cycle has no choice. It has to it has to travel on a row from left to right. It's allowed to go and make side trips to closures, but it must come back to the next vertex on the row and traverse all the vertices on the row in the same direction. So that's what we just argued. And now we are in good shape, right? Because now we can extract the assignment, right? How do we extract the assignment? Well, you look on the Hamiltonian cycle, you look on a close, right? The Hamiltonian cycle must visit every closed vertex. As it visits it tells you what the assignment is, right? If it's visited in like that, then you know that it's being satisfied by, in this case, x4, right? And x4 is assigned, in this case, a 1, right? Being from left to right means 1. So x4 satisfies this original clause. And more importantly, because of the no shenanigans, we know that every row is being traveled from left to right. So now what we can do, we can just remove this closed vertex. We say, okay, x4 is traveled from left to right. As such, x4 is assigned 1. And now we can just remove this detour for this clause, because this clause is now satisfied, and go straight. Just use the edge directly to travel straight, and we get this new Hamiltonian cycle in this new graph where the closed vertex was removed. And now we repeat this process. We keep removing vertices, And once we do that, right, what we remain with is the original frame graph with a valid Hamiltonian cycle, which gives us the assignment for the variable, which is what we use to satisfy all the clauses. And now we are done, right? We found an assignment to all the variables, and this assignment satisfies all the clauses. The end. If there is a Hamiltonian cycle in this graph, well, not in this graph, but the original graph, right? If there is a Hamiltonian cycle, if there is a Hamiltonian cycle in this graph, then by necessity, there is a satisfying assignment to the original formula. Okay, so this is the proof. Right? We just proved that if the graph has a satisfying has a Hamiltonian cycle, then the original formula has a satisfying assignment. Now we can combine this to conclude that the computed graph has a Hamiltonian cycle if and only if the original formula is satisfiable. So we proved the correctness of the reduction, right? Now, this proof and reductions were not easy. This is a clever reduction that clever people came up with. We are not going to expect you to be able to replicate this kind of a reduction on your own, right? So this is just an example of seeing what tool you can use, and of course see that this problem that is very interesting, Hamiltonian cycle, is NP-complete. Okay, so let's summarize. We showed that the Hamiltonian cycle is in NP, directed Hamiltonian cycle, doesn't matter. We provided polynomial time reduction from 3-sat into Hamiltonian cycle, and we proved that the reduction was correct. And as such, we now get the result that Hamiltonian cycle is NP-complete. In this case, it should say directed. All this slide should say directed. Which is what we wanted to prove. So the end for now.